there, and welcome to day 21 of the 24-day extravaganza of physics questions. Today I have one solely on nuclear decay. It does have a slight smidgen of first year physics with a bit of a beta equation, but it's predominantly a second year thing with nuclear sort of decay equations and nuclear reactors. Okay, it's got a really unusual error as well in it. I'm going to show you what it is in a minute, and it's something that you can be aware of when you're doing your papers. So we've got here a rod named of uranium-238. So it's called uranium-238 because that's how many nucleons it has in it. And you can see that up here. That's how many nucleons it has in it, okay? So it's got 238 nucleons. It's placed in the core of a nuclear reactor where it absorbs 3 neutrons. When a nucleus of uranium-238 absorbs a neutron, it becomes unstable and decays to neptunium-239. You can see here the 239 neutrons, which in turn decays into plutonium-239, and for some reason they've written 293 up here. So this is actually like a really weird error in the actual paper. And so it's just something to be aware of. If you see things like plutonium-239, that's how many nucleons it should have. So it's asking you now to write down the nuclear equation that represents the decay of neptunium-239 to plutonium-239. So I've got neptunium 23993 decaying into plutonium 23994. So this is important. The nuclear number hasn't changed, so that there is still the same amount of neutrons and protons added together, but the proton number has changed, which means that a neutron must have turned into a proton. And of course, that means the only decay that could have been is beta minus. So this is the kind of decay you get, beta minus, so that's 0 minus 1, plus, of course, to balance that lepton number, you need anti-electron neutrino. Okay, there's 2 marks available, one for realising it was beta minus decay, and 1 mark for actually filling the equation out fully. Okay, so now we've got a graph here. A sample of the rod is removed from the core and its radiation is monitored from time t equals 0. The variety of the activity is shown in the graph, okay, and I've got activity versus time. And it's showing here, and you can see it's an exponential because it's decreasing like that. Show that the decay constant of the activity sample is around about 3 times 10 to the minus 6, okay? So this is one of those things you go, oh, I don't know what to do here. So let's actually break this down. So we've got activity, and activity, of course, is activity equals n lambda. I'll just change back to my red pen. So, but the thing is, I don't know how many nuclei I've got, so I can't use that information to work out the decay constant. So what else have I got? Well, I know that the decay constant equals ln2 over the half-life. Now, because I've got a graph, I might be able to work that out. So let's actually work out what my half-life is from my graph. So it starts at, you don't have to start at the top bit. You can actually start at any point. So what I'm going to do is I'm going to say when it's 4, okay, that's 0. So I got when t equals 0.2, activity equals 4. So I'm going to half that and go here. So when t equals 2.2, activity equals 2. So my half-life from that information is going to be 2 times 10 to the 5 seconds, okay? So let's actually use this information. I've got my half-life here. So I'm going to do decay constant equals ln2 over 2 times 10 to the 5. I'm going to bung that into my calculator. I end up with, I've got 3.47 times 10 to the minus 6, which is a little too big, but you could argue that the sample is 3.4 times 10 to the 6. So what happens on this one, what I'm going to do is I'm actually going to do it again. So it's not as close as I would like it to be. So you know what, I'm going to actually work it again. So you would actually get a little bit more room in this question. I'll just cut it up a little bit. So let's go from up here. I'm just going to do this one up here. I've got t, when t equals 2.2, my activity is 2. And then I want my time when my activity equals 1. So let's do that here. So I've got here, when my activity, when my time is 4.2. So again, my change in time is going to be 2, and that's my time half-life. So I've done it twice now, and it's showing me the similar answer here. So it's approximately about 3.4. It's actually a little bit too big. But it's within the realms of possibility because, of course, I'm rudimentarily reading things off a graph, trying to make sure that they're correct and not zooming in. So that's actually what the example was to see. If I actually show you the mark scheme for this, so you can actually see what I mean. So I've done that here is like the T2 to 2.1, time to half-life 2 to 2.1, which is what I got, okay? And then actually putting it in, okay? Or substituting 2 points into the activity. They say both alternatives give 3.3 to 3.5 times 10 to the minus 6. So my 3.47 is actually within the mark scheme's valid reasoning. So my method, though a little bit off, don't be too scared if your number is off like that. They're saying it's about 3.4 and you get 3.47. There's normally, especially with graph reading things, there's normally a massive margin of error. And the fact that I got 3.47 times 10 to the minus 6 in the great scheme of things, it's not that far off 3.4. Okay, if you got 3.4 and your answer was like 4.2, that's really far off. But that kind of realm isn't that. So don't be scared if you get a little bit off like that, okay? So, assuming the activity comes from only decay of neptunium, estimate the neptunium number and nuclei present in the sample at time t times 5 times 10 to the 5. So what I'm going to be using here is the formula A equals A naught e to the minus lambda t, because I want to actually get a really good answer. So A naught is approximately, going up here, 4.25, okay? So it's approximately 4.25 times 10 to the 12, okay? I need to find my activity because I want the number of nuclei. And remember, I said earlier that activity equals n lambda. So if I can find the activity at that time, I know how many particles I had. I know my decay constant is about 3.47 times 10 to the minus 6, and my time is 5 times 10 to the 5. So I'm going to put this all into my formula. So I end up with 4.25 times 10 to the 12 e to the minus 3.47 times 10 to the minus 6 times by my time. I'm just going to put that into a calculator. So times by 5 times 10 to the 5. Oops. So 3.47 times 10 to the minus 6 times 5 times 10 to the 5. Minus that. E to the power of that, and then times by 4.25 times 10 to the 12. So I've got an activity of 7.5 times 10 to the 11. And you know what? Having a look up here, it's a little, about 7.5. Yeah, it's about right. Okay, you could have used the graph. So activity equals n lambda, so n equals A over the decay constant. So I'm now going to divide that by my decay constant of 3.47 times 10 to the minus 6. And I get an answer of 2.2 times 10 to the 17. Of course, there's a line, you must put it in there, so 2.2 times 10 to the 17. Now, if we actually have a look at the mark scheme for this on here, going down, again, it's because it's all graph data, they're allowing all sorts of weird information. So they've got using A equals n lambda, and they were using data from the graph. I actually used A equals A naught, which is a perfectly acceptable way to do it as well. So I got allowing anywhere between 2.2 and 2.4 times 10 to the 17, I got 2.2. So I got that right there. It's just a weird way of doing it, especially with graph data. There's normally multiple ways of doing it, and there will be multiple interactions here. Okay, so let's go back to this question. So now we're on to an explain question. So a chain reaction is maintained in the core of a thermal nuclear reactor that is operating normally. Explain what is meant by a chain reaction, naming materials and particles involved. So a chain reaction, of course, is when one neutron goes in, gets absorbed by a material and becomes something else. And then what will happen is the decay, when it decays, it releases more neutrons than it actually absorbed. Okay, so what we've got here, so we've got chain reactions made to the core from reactor. So actually, when you have a thermal reactor, you've got your. So what's weird about this answer is it talks about uranium-235, which is normally what I would argue that is, but it says here that the uranium. Let me write what I would write. Okay, this says uranium-235, which is confusing since it's talking about uranium-238 in the question. And I just want to highlight that again. This question had a few errors in it, which I was a bit confused about. So what actually happens is the uranium absorbs one neutron, and when it decays, it will emit more than one neutron along with its daughter nuclei. Okay, so what's actually going to happen is uranium. So I'm being loose in the. I don't know why it says 235. I would normally expect it to be 235, but it talks about 238 in the question. So a bit confusing there. But the idea is that when uranium absorbs the neutron and then it decays, it will emit more neutrons than it absorbed. Okay, this causes more reactions, and they will grow exponentially. So currently, while I'm actually doing this whole thing, it's actually during the 2020 COVID pandemic, and this is the whole idea of what our number is about. Our number is about if you are infected, how many people are you going to infect? And when it's more than one, that's when the R number is bigger than one. So you're actually, what will happen is an exponential increase in transmission of a disease. In terms of nuclear, that's exactly kind of what's happening here, that you have one neutron hitting uranium. And if only one neutron was emitted from that, you would have this steady sort of just what's happening here. But if one neutron hits it and you get more than one neutron emitted, that you got one going to three, okay, and each of those three going to another three, and that is what we call a chain reaction. It becomes very uncontrolled when you get exponential. You have a growth in exponentially there, okay. So you go to the mark scheme of this one. It does mention 235, which I find really strange, but it says uranium and a neutron. Okay, so it captures a neutron and splits into two, releasing more neutrons. Okay, at least one of these usually goes to force for splitting of fusions. So you get the second mark for releasing, which causes more fission. Okay, so I kind of mentioned that, said in case emitting one neutron which hit with its deuterium, this causes more reactions and they'll grow exponentially. So that's kind of what I'm implying by that. Could have been a little clearer by saying that these because of more collisions. I could have been a little clearer. Okay. All right. So explain what the next question is. Explain what the purpose of a moderator is in a nuclear reactor. So a moderator is there because it removes. So what a moderator does is it moderates the reactions. Okay, the control rods are the ones that control the actual neutrons that are emitted. The moderator, it removes kinetic energy from the particles. Oops. Which controls the amount of reactions. So go to the mark scheme of this one. Okay. Interestingly, they say here, see this thing here I've mentioned, the moderator slows down, reduces the kinetic of the neutrons, so the neutrons are absorbed, react efficiently by the uranium. So I'm talking about the fact that it slows down the amount of reactions, okay? But I've mentioned about the moderator slows down and reduces the kinetic energy there, okay? It does talk about critical mass. I do understand about critical mass, but it's not something that I would have actually brought up in this question, and I understand some people would. But when it says escalate in an exam mark scheme, it means that it would have gone to another examiner to actually check your answer. Okay, because you can waffle about physics, but it might not be correct physics, which is why it needs to be escalated. Okay. Lastly, substantial shielding around the core protects nearby workers from the most hazardous radiations. Radiation from the core includes alpha and beta and gamma particles, X-rays, neutrons, and neutrinos. Explain why it becomes radioactive. So for something to become radioactive, it must become contaminated, okay? So explain why the shielding becomes radioactive. And it's because the shielding is absorbing the material. So what if you look at the mark scheme here before I write it down, it says neutrons are absorbed by the material, converting the nuclei into unstable isotopes. So let me explain that and actually put that into the way I would have put that into an exam question. Explain why the shielding becomes radioactive. So to become radioactive, it means elements in the shielding have become unstable. Okay, so it can mean it could be that it's contaminated with something, or it could be, in this case, they're mentioning about there's flying neutrons around. Okay, but the idea is that to become radioactive for something that has to emit radiation, you must have either something about you that's unstable, so being contaminated by some of the materials, or the elements have become unstable. So to become radioactive means the elements have become unstable. This is because, and again, it's an explain question, so using the word because, elements in the shielding have absorbed excess neutrons, becoming unstable isotopes, which would decay. Okay, so what this is talking about here is like it wants you to understand why would something become radioactive. You need to understand that something is radioactive when it is an unstable element. Okay, so that either means the material contains unstable elements or the elements become unstable. Okay, and what's actually happening here is the elements inside the shielding are absorbing the excess neutrons from the actual reactor. And then what's happening is they themselves are becoming an unstable isotope, which is decay and emit radiation. Okay, so checking that mark scheme again, neutrons are absorbed with the shielding, convert a nuclei into unstable isotopes. Okay, so it's a really tricky question, but it's down to the crux of this idea. Do you understand why something is radioactive? And it is radioactive because it is an unstable isotope. Remember, if you have not done this yet, you will be doing it along with radioactivity. You've got an NZ graph here, and you've got your NZ line here. And this is, so if I actually just draw what it's supposed to look like. Oh no, this one's supposed to be a dotty line, sorry. So this one here, this is the N equals Z line. And elements do that. Okay, it's probably a little less steep than that. But what this here are all the elements that are on the periodic table. These are the stable isotopes of elements. Okay. You'll have elements that have more sort of protons, or you have some elements that will have more neutrons than they should. And they will all decay back to try and get back to that stability line there. Okay, so a really rough graph. You can watch the video on NZ graphs in my radioactivity playlist, and that will give you a little bit more information. But this idea of something is radioactive because it is an unstable isotope. And so there you have it. There's quite a wordy bit on the end, a question on nuclear decay.